In this video, we're going to make an introduction to vectors. So suppose we are told a person starting at the origin here, and they travel 5 kilometers on the first day and 6 kilometers on the second day. Well, the question is that enough information to determine where the person will be? Well, definitely not, because 5 and 6 are just regular numbers, also referred to as scalars, and these things can give lengths, but they don't contain any directional information. So you can see that there's a need for us to make new mathematical objects that can somehow communicate length and direction at the same time. And the simplest and the most obvious way that we can actually achieve this is for us to draw arrow diagrams. So the length of the arrow obviously indicates the length, and the direction is indicated by the direction that the arrow itself is pointing in. So you can see that if you follow this arrow of length 5 and this arrow of length 6, we can easily tell where the person will be. We have a fancy word that we can use to refer to arrows, and that's the word vectors. Next, let's talk about some basic notation. So we typically use these pronumerals to denote regular numbers, but because vectors are new objects entirely, they're going to need a new set of notation to differentiate them away from numbers, so we don't get them mixed up with these things. So suppose we wanted to label this vector here, what we can do is write a pronumeral, but now with an arrow directly on top of it, so that it looks different to these things. Other typical ways that we can describe a vector, we can write it like in these manners. So vector A, vector B, vector V, vector X. People also, instead of drawing an arrow on top, they draw squiggly lines on the bottom to indicate the same thing. Within textbooks, vectors are typically indicated by using boldface. This is because writing squiggly lines on the bottom and drawing arrows on top is very difficult to type. Okay, next let's talk about the notation behind describing the length of a vector. So the length of the vector A is denoted like this. So what you do is you write the vector first, and then you surround it with some vertical bars. So suppose we got a vector here and its length is 5. Then we can write that symbolically like so. What's really important about this notation is that we need to stress that what comes out of this symbol here is actually just a regular number, because the symbol is saying the length of the vector, and that is going to be some regular number and not a vector. Next, let's talk about the 2-point notation. So suppose we got 2 points in the plane, point A and point B. Well, we can connect them using a vector. In this case, if we're trying to name the vector, we will name it as vector AB and write it like so. And you can see that once you have drawn a vector has a tail point and it has a head point. And under this notation, if you wanted to write up the length of the vector, we'll write something like this. If the length of this vector was 5. Next, let's talk about when two vectors will be equal. So the thing about vectors is that a vector only has two determining features, its length and its direction. So what this means is that two vectors will be equal if they have the same length and direction. So if I got these two vectors here, vector A and vector B, you can see that these two things have the exact same length and they point in the same direction as well. So based on that, we can say that these two vectors are equal. That is, vector A is indeed equal to vector B. Okay, let's see what happens if we take this image here, these pair of vectors, and we place them inside a number plane. And the question is, if you look at this image here, would these two vectors still be considered to be equal? Well, definitely yes, because it's exactly the same two vectors as per the previous discussion. And when I moved it into this number plane, really nothing's changed about them. The length's still the same, they still point in the exact same direction. So of course these two vectors are still exactly equal. But however, this image causes some confusion sometimes. And I think that confusion originates from these sort of things. That's because when we learn about basic line equations, these two lines here, they have two different equations, and they're definitely considered to be two different lines entirely. Whereas if we look at a kind of a similar image but now involving vectors, these two vectors are now considered to be equal. And again, that's only because how do we check two vectors are equal? We just have to check the fact that if they have the same length and same direction, so they will be equal. Next important property about vectors that we should discuss is the fact that we can pick up vectors and move them around. So I can pick up this vector A here and move it around like so. And similarly to before, despite moving it around like this, we obviously haven't changed the length or direction of this vector. So this vector, despite being moved, and despite also pointing to a different location now, it is still considered to be the exact same vector that I started off with. So it still deserves the same name. It is still the same vector A. Okay, let's look at this scenario now. So we've got these two vectors starting to be equal here. But if I take vector B and I tilt it even a tiny little bit, now definitely the direction of these two vectors are different. So now these two vectors are definitely not equal anymore. Now let's discuss the notion of vector addition. So we are familiar with numbers as mathematical objects. And with numbers, we have the addition operation that allows us to combine two numbers, giving us a third. But right now we have introduced a brand new set of mathematical objects, these vectors. But right now we don't have an operation to go with them. And in the case of numbers, having the addition operation and other operations is what makes them useful. So if we left things as it is, like there's no operation to go with these vectors, they're not going to be very useful. So what we're trying to do is define what would it mean to take two vectors and add them. In the case with numbers, we had two numbers, you can add them to produce a third. So we're going to define this in a similar manner. So what happens if we add two vectors, we should produce a third vector. So the question is, what should this third vector look like? How should we define this thing? Let's start with a simpler scenario where the two vectors where we're trying to add points in the same direction. So in this scenario, it's pretty intuitive to take this vector here and place it against the first one like so. So placing the tail of the second vector against the head of the first one. And just from this image, it's pretty intuitive again to define the sum vector as this one. The vector that runs from here all the way to here. So the green vector is the resulting sum of adding this one with this one. So what's the actual procedure that we've just gone through? It seems like when we try to add these two vectors, vector A plus vector B, we had to take vector B and place it against the head of vector A. And the resulting sum vector is the vector that starts from the tail of the first guy and runs all the way to the head of the second guy. So now that we have this sum procedure, let's apply it to a general scenario where we have any two vectors. So let's go through the procedure. So what do we have to do? We're trying to do vector A plus vector B. So we're going to place the vector B on the head of the vector A. So it'll look like this. And the resulting sum vector is going to be a green one that's going to start at the tail end of A, going all the way to the head of this vector B here. So the sum vector will look like this. So this procedure, this box here, we're going to refer to it as the head to tail definition of a vector sum. Okay, so we define the notion of a vector addition and it looks like this. Oh, just one more minor thing before moving on. So the minor thing is that these two symbols here, they're the exact same symbol, but really they mean two entirely different things. One is the addition symbol that allows us to combine two numbers, while this one's the addition symbol that allows us to combine two vectors. So kind of technically they really deserve two different symbols, but if we come up with too many different symbols, things look messy, and we just recycle and reuse the same symbol anyways, because they communicate the same thing. They're the same in essence in the end anyways. Okay, now let's look at what happens when we're trying to add these three vectors together. So let's add these two first. If we wanted to do that, we'd do the head to tail thing. And the resulting sum vector from these two is going to be this one. Now we want to add the green one as well. So we take this green vector, place it against the head of this intermediate sum vector. So it will look like this. And the final ending result vector will be the sum of this one plus this one. So the final answer is going to be this vector here. But after doing all that, you realize, well, we can actually just skip this intermediate one. If you want to add three vectors together, just chain them together like so. And the final answer, the final vector, is going to be the one that goes from the tail of this red one all the way to the head of the very last vector that we were trying to add. Okay, the next thing to talk about is commutativity. Well, number addition is commutative. What that means is that if you try to add two numbers together, you can just do that in whatever order you prefer. You can do a plus b or b plus a, it wouldn't matter because the end result is equal. They're the same. So the natural question to ask now is, we define vector addition, and the question is vector addition itself commutative? That is, when we do vector a plus vector b, is that going to produce the same result as doing vector b plus vector a? Okay, let's try and investigate this question. So we're going to try and do a plus b first. So we're going to start with the vector a, and to add to b, we'll place b here like so. And the resulting sum vector is this one. So this is the result of doing a plus b. Now let's do b plus a. So now we're going to start with b first, and we'll try to add to a, so we place a like this. And you can see visually we're going to end up with the exact same answer as before. So indeed, vector addition is commutative as well. Okay, so realizing this result also gives us another way of actually visualizing vector addition itself. So the old way, the previous initial way of looking at vector addition is this. You do the head to tail thing, and the final sum vector is like so. But after discovering the commutativity diagram, we can also add vectors like this now. So before it was placing vector b against the head of a, but now we're going to take the two vectors we're trying to add, and we can place them tail to tail like so. And you can see that when you do that, the two vectors actually span a parallelogram that we can imagine. And the resulting sum vector is actually the diagonal, this particular diagonal of the parallelogram. Now we're going to talk about two special vectors, the zero vector and the negative vector. So within the number system, we have a very special number, the number 0. And the number 0 plays this role, the role of the additive identity. What this means is that 0 is effectively does nothing when you apply it within an addition. So when you add 0 to any number, the number won't get affected, it will just come back out. So the question is, within the vector system, is there something called the zero vector, written like this, that is able to play the analogous role, this role of the additive identity? So we're looking for a special vector such that when we add it to any other vector, it's not going to affect it, it will just return the same vector back. And if this vector does exist, well, what does it look like? The next important role is the notion of additive inverse. So within the number system, for any number a, there's a corresponding negative number written as negative a. And this is the special number such that when you add it to a, you get the additive identity back. So we're going to ask the same question, but now for the vector system. That is, if I draw up any vector a, is there a corresponding negative vector written like this, such that when I take it and add it to a, we're going to get the 0 vector back. And also, if this negative vector does exist, well, what does it look like? Okay, so we're going to answer both of these questions with one example. Suppose we've got this vector a here. We can draw a vector that has the same length, but pointing in the opposite direction. Well, we're going to ask, what happens if we try to add these two vectors together? If I do the head to tail thing, like lining them up head to tail, these two vectors actually line up perfectly when we do that. And what is the resulting sum vector? Well, we got to go from the tail of the blue vector to the head of the red vector. But in this special case, you can see that those two locations are actually exactly the same point. So the resulting vector is a very special one. It's a vector that's been collapsed entirely down to a singular point. So due to the way that we have defined vector sums, this definition actually gives existence to this very special vector, this vector that's been collapsed down to a point, and hence it has 0 length. And because it has 0 length, it can't specify any direction. So we say its direction is undefined. And you can see that this special vector clearly is the 0 vector, because it has this property such that when we try to add it to any other vector, it's not going to affect it. It's not going to affect it because itself has 0 length to it. So when you add, nothing's going to happen to it. Okay, so we actually answer the other question involving negative vectors as well, because this vector that we originally started off with, if we take it and we add it to vector a, we do indeed get the 0 vector out. So this red vector here has this particular property. So what that means is that this vector here really is the negative of this vector. So negative vector will be the vector that has the exact same length as this, but pointing in the opposite direction. Okay, so we answered both of these questions now. So the 0 vector does indeed exist. It's the special vector that's collapsed down to a point, and it has 0 length, and its direction is not defined. And it has this property such that when we add it to any vector, nothing's going to happen to it. And we answered this question as well. For any vector, there really is a corresponding negative vector as well. And the negative vector looks like this. It has the same length, but points directly in the opposite direction compared to A. And it has the property such that when you add these things together, you're going to get the 0 vector. Next thing to talk about is scalar multiplication. And remember, scalar is just a fancy word referring to regular numbers. So all this is saying is that we're going to take vectors and we're going to see what happens when we multiply them with regular numbers. So we know how to add any two given vectors, but what happens when we try to add a vector with itself? Well, symbolically, this guy definitely deserves to be written as 2 times the vector, 2a. And let's see this geometrically. So we're taking a vector and adding itself to it. So the end result will look like this. So this is the vector 2a. So you can see that when we take a vector and we multiply it by a scale of 2, what happens is we're stretching the original vector and stretching and increasing its length by a factor of 2. So just from this example, we're going to make a definition, and that's going to be when we try to multiply a vector by a scalar lambda, we're going to scale its length by a factor of lambda. Okay, let's apply this situation to other scalars. So what happens if we look into half of A? Well, we're going to scale its length by a factor of half. So we're not only enlarging vectors, we can also shrink vectors as well. What happens if we try to multiply a vector by the number 0? Well, we're scaling its length by a factor of 0, so its length is going to disappear completely. So this is going to contract down to the 0 vector itself. What happens when the scalar that we're using is actually negative? So when we look into negative 2a, that can also be written as 2 times negative of a. And multiplying by a positive scalar, we know how to deal with. So suppose this was vector a, and we're trying to look at what minus 2a looks like. Well, this is suggesting that we should start by looking at the negative vector first. So that's this one. The vector with the same length, but pointing in the opposite direction. And we're multiplying it by a positive scale of 2. So we're going to scale it and increase its length in the current direction by a factor of 2. So this is the vector negative 2a. So summarizing, if you take a vector and multiply it by a positive scalar, it's going to scale it by that factor in its current direction. And if you use a lambda, a scalar number that's negative, you still scale its length, but this time the factor is determined by the absolute value of your negative number that you're using. So you scale by that amount, but at the same time you completely reverse its direction as well. So just from these images, you can tell that all these vectors all deserve to be called parallel. Like this is obviously parallel to that. In fact, they are in the same direction. These two vectors are in completely opposite directions, but they still can be referred to as being parallel. So we make another important definition, and that is we're going to say two vectors are parallel to each other if and only if it's possible to scale one vector into the other using some scalar multiplication. Now we're going to mention one specific application of vectors, that is using vectors to describe position, so the notion of position vectors. So suppose we got some point A within the number plane here, and we got the origin here. What we can do is draw a vector from the origin to the point A. And this vector here is going to be named as the vector OA. So when we're using vectors in this manner, we're going to refer to it as the position vector of the point A. But the important thing about vectors is that, remember, we can pick up vectors and just move them around all we like, move them around, use it for various purposes, use it within a vector sum, and so on. But it's really important to know that once we've picked up the vector, once the tail leaves the origin itself, we're actually not using the vector to describe positions anymore. We're not using it as a position vector. So once we've taken this vector OA, we moved it off. Notice how it's now pointing to a different location, some point B. But this is not the position vector associated with this point. So the rule is, if you want to use vectors to describe locations, you want to use it as a position vector, the rule is you have to pin its tail against the origin here. So the position vector of the point B will look something like that. And that's the vector OB. But at the same time, remember, we can take vectors and just move them around. So right now I could move these two vectors off. I can move this blue vector to here. I can do things like vector sum and so on. It's just that if you want to use vectors to describe locations, so we're using it for this specific purpose, if you want to do that, you have to pin the tails of all the vectors down into the origin like so. Let's summarize these results. So vectors are just arrows which have length and direction. And to specify length, we use this sort of notation. And these are the only two features of vectors, meaning two vectors will be equal if they have the same length and direction. And we got to remember that we can take vectors and just move them around. And next we define vector sums using these diagrams, with the vector subtraction as a special case of a vector sum. And we also discovered two special vectors, the zero vector, and for any given vector, we can also construct its negative vector. Next, we looked into what happens when we take a vector and we multiply it by a scalar, so a regular number. And if the regular number is positive, we just scale that vector, we scale its length by the factor determined by that regular number. And if that regular number is positive, we scale in its current direction. And if that number is negative, we still scale by this amount, by the absolute value of this thing, but reverse the direction of the vector itself. And this notion gives rise to the definition of what it means for two vectors to be parallel. And lastly, we looked into using vectors as position vectors. So vectors can describe positions, but only once when we take the tail and pin it down into the origin.